All right, we're going to start our lab on flip-flops. We're going to start with the SR flip-flop. I asked you to explain the difference in SR or latch and SR flip-flop. That's explained in the text, and you can look it up. I want you to just look it up and then a sentence or two explain it. Go fill out the truth table. Now, originally I was going to do this with you. Unfortunately, I did it, and then we had a technical issue that happened. So I've got it. Went ahead and filled it out. So S, R, if there's 0, 0, we stay the same. So Q stays Q, Q naught. The little apostrophe over here is just a way of using a standard character for the little line over the top. We can call that state latch. If you want to call it memory, you can do your own words. The key is that holds what the previous value was. Sometimes you'll also see it written as something like Q of n equals Q of n minus 1, or Q of n plus 1 equals Q of n. Just showing it stays the same. 0, 1. Resets Q to 0. So you can set Q equals 0, Q equals 1. If S is 1, 0, you can call those reset and set. Those are the conditions to set specific values. With SR flip-flop, if both inputs are 1, the output is invalid. It'll actually set both to 1. So this first page is to fill out to let us know what we need. I put 5 entries on this when I wrote this. I'm not entirely certain why, because we don't really have a good use for that last one, so you can just skip it. Okay, now if you go to the next page, you'll see the table again, but what I tell you is construct it using a 74LS100 quad NAND chip. So what we're going to do is construct it, then we're going to go through and test this. Then we're going to see if it performs like the theory. And I'll tell you, it should work just like the theory. If you got your theory right and you build it right, it'll work like it. And that's the reason we do this, to reinforce that. So on the breadboard, or on the trainer, I've gone ahead and put power. I put ground. I put my 7400 chip down. Okay, I've gone ahead and set voltage. I'm going to remind you, check this closely. You don't want to run voltage in here if it's set up at like 15 volts. When I first built this, that had been left 15 from the previous lab I had recorded. And I just turned it all the way down and then measured it with the multimeter and set voltage. So I'm already set at 5. I'll come in and just put ground, so I have ground. And I'll put positive up here. I'll turn power on. I'll double check this. Okay, now what I want to do is build my circuit. So I'm just going to lay the circuit up where we can see it and talk through it. Okay, so I need S as an input to a NAND gate. Now I'm going to choose the NAND gates on the bottom side of this for this only because I know what's happening after this first part of the circuit. If you build on the top, that's fine. Remember, we have an input 1 and 2, output 3 for the first NAND gate. So I'll just do that. I'll use A in place of S, and I'll use B in place of R, and I'll run that into the next NAND gate. So this is input, input, output, input. It's a very long... I'll take it up here. Okay, and I'm going to bend those two inputs kind of off the board so they're out of the way so we can see what's going on. Okay, now my output of S is the input of R. So the output here, pin 3, is the input, the other input, so it'll be 4, 5. And I would note, if you're curious, it doesn't really matter which input I use for the S part coming in, which one I use for feedback. They just have to be the opposite. So I took my output of the first one, and it's the input of my second. Likewise, my output of the second flip-flop, which is all the way over here, pin 6, has to go back into pin 2, the unused input. So you can see there, I have 2 inputs here in the feedback, 2 inputs here in the feedback. Okay, now the last thing I have to do to get my SR flip-flop to work is to run up to a couple LEDs. So this is Q naught. However we built this, we ended up with it already lit up. And this is, in fact I can stick it under here close, Q. Okay. Now we want to test it. Now, I'm going to let you know something here. Most students would build it this way, and it will be perfectly fine. However, your truth table wouldn't perfectly match this, and that's because this input, while it's an SR flip-flop, it's SR latch, but anyhow, R and S are R0 and S0. To account for that, I can either in my mind shift them, or because I'm using these logic gates at the top, I'll just plug in and, I have, instead of A, I'll use A0. Instead of B, I'll use B0. Okay, there we go. Lights are on, so I'm going to go through and check this. You want to fill out that next truth table as you work through it, but I'll just check against this so we can see it. So if I start at the top, 00 is latch or memory. Hard to tell. So let's go down, because it's got to just keep with the last value. So we'll check it as we go. So we'll go down S0R1. 0, 1. That should set this Q to 0, Q0 to 1. Since it's exactly the same, kind of hard to tell. So let's go try here. 1, 0 produces 1, 0. 1, 0, 1, 0. So through 0, 0, it keeps my memory. So I'm checking that. 0, 1, we'll flip it back. 0, 0 will keep my memory. If I go up to 1, 1, I get all 1s out, which is my invalid. So when I do that, I can just fill out this table on page 2. I'll just fill it out, and I'll show that it works exactly like the one on page 1. And again, your S and R will be inverted if you connect those so they're positive high. The default is positive low. Does it perform according to theory? I ask those questions so you can go back and answer them and say, yes, it does perform to theory. You should, briefly explain why. If you have any discrepancies, talk about them. This is where you would say, for example, I used S and R instead of S0 and R0, and here's what happened. Either way is fine. All I want to do is make sure you understand it. My goal of this is not busy work. The goal is that you understand it. Okay, connect the reset to the clock on the trainer. Observe what happens. So my reset input, which we're using as B, I'm going to take over. I have a clock, 60 hertz. That's not what I really want, though, in the middle. But on the outside, I have the positive and the negative side of the clock. And what I'm going to do is take it over here to the 1 hertz. So 1 hertz means it's cycling once a second. So I can actually see what's going on. If I go higher, I can't really see it. So I'm going to try this. This one won't matter, but if this is 0, 1, or 0, 0, either way, it stays here. Flip there, sets this 1, 0, or invalid, because this is going back and forth. So I can observe what's going on and talk about that. Okay, when I'm done with that, what I want to do next is we're going to use all 4 gates to build an actual SR flip-flop. So I'm going to use the 2 other inputs as, or the 2 other NAND gates as inputs to my current existing circuit. So this one with the hashes around here, we already built. That's what's going on the bottom. All I need to do is my inputs now need to come from the NAND gates, the other 2 NAND gates. So I'll take them from the far side of my circuit. So I'm going to remove these for now. We'll come back and add them in a second, but this will be SR. And now we're using actual SR instead of S0 and R0. So I'll move them over there. We're ready to go. I'm ready. Now I just need to get to the other side of this. I'm going to have an output from this NAND gate. Input, input, output. This wire may have gotten used more than it can take, but it's not feeling very good. Okay. Okay, these are a little longer wires than I'd want, but they'll hop back over and do the job. So this input comes from the output from this buffering NAND gate on the far side. The input to that NAND gate is S, so I'll take it using A in place of S, or for S. And the other input is the clock. So we'll put a wire over here for the clock. So let's take the clock down. And right now I've hooked this up. So you can see I have clock in, S in, just like we said, and the output runs into this NAND gate. Okay, now the other side. we need clock in. So I'm going to take the clock down here. I don't need two going all the way up to the clock. I'll just take the clock right here and hop it over. So there we go. That's an input from the clock. R goes into the other input for that NAND gate. So I have a clock in and R. And now finally the output of that has to go into the output for R. Now, one of the things you can do with this, I didn't do it here, but you could go through and list these. Like, power is 14, so I might put, okay, this input is, okay, it's hard to do. I'm going to write to the side. I might say, hey, this is 13, this is 12, this is 11. I'll show you here. So I might go over and just hold them up next to my pinout and say, hey, 12 and 13 are inputs to this top left NAND gate, output's 11. The one on the top, 9 and 10 are inputs, output is 8. So write them on there. And then on the bottom side, I'm hopping them over to, see, that goes to 1. Three. Might have one of these off when I did, because I just kind of did them off the fly. And again, I just took these off looking at the pinout, and I just label them. And that way I have a connection number, and I'm not looking back and forth to the pin. I'll use the pinout to label these numbers, and I use these to actually build it. Okay, now that I build it, how does it work? So 0, 0 should be latch. 0, 1 should set that. Right? It's a 0 out for Q. 1's Q naught. 0, 0's latch, hold it. 1, 0 will flip it. One of the nice things about staying at 1 hertz is you'll notice, well, that one went right away. They're all right now when I'm trying to explain it, but sometimes you'll see that little time it takes to go. If I take them both up, you'll see it sets there. It actually might start flashing at you because of the clock signal doing what it's doing, and that's fine, but still an invalid state. Now you can have fun and put it up to 1 kilohertz. Here's what will happen. Everything will happen so rapidly you'll never see that delay. So at 1 hertz, you should occasionally be able to see the delay if you play with it. Going at 1 hertz, though, sometimes it moves as rapidly as you do. All right, so this is an actual SR flip-flop where I have inputs S and R. I have a clock, so it actually only triggers on the clock itself. So you want to demonstrate that. Okay, now I have this built. I've got my SR flip-flops built. So the next thing I want to do is build the JK flip-flop. Now, it's very tempting to think I have to tear everything apart. But I will note, I'm not going to build this one for you. I'm going to let you do it because we've already done so much, that this part right here is my base SR flip-flop I started with in the very beginning. Over here, this is really like the flip-flop I just had. Now, the problem is I need 3 input flip-flops, so you need to get a 74LS10 that has 2 triple 3-input NAND gates and use it. So you'll put alongside here, get power. You'll disconnect what's going on in the top, and you'll run these over to that other flip-flop. So I'll keep my power here, but my feedback will come off the other chip. So what I want you to do next is go through and just use those 2 together and build this. Up here, go ahead and go through and put your JK truth table down. So 0001, 1011. Repeat it. This is just clocks, so showing the clock signal going positive. So typically we would write this like this. When I'm here, I'll move those wires out of the way. In fact, I'm going to move the whole board out of the way. I should have done that. So what I did is I came down here and I said, hey, this is 0, 0. This is with the clock going high. Clock is, maybe you even want to just put 1 here because that's the way this will work. This is going to stay the same. That's the previous value. That's previous value. So your latch state. You're going to have a, Q is 0, Q is 1. So that's going to be, set and reset. Look them up, what they say they are. Use them. 1, 1 is going to be toggle. Right, so Q in is equal to the last one inverted. Okay, if you're not doing this, what these should all show is that it stays exactly the same. So you could put, hey, this just stays at Q. This stays at Q naught. And you can just go down and put no change. So you'll see this a lot of times in what's called an excitation table. All they're recognizing is this is my truth table for JK when the clock goes to trigger it. A lot of times they'll show an up arrow, which says it's going on the positive edge. A down arrow is on the negative edge. Ours is actually, while we drew this as a clock, this one will actually work as what we call more of an enable, which means if this is 1, stuff happens. When it's 0, stuff won't happen. So build it, connect it for the 1 hertz clock, and then go through and analyze it and make sure it meets that. That's all we're doing in this case. Does it work according to theory? If not, consider any errors you made and fix them. Explain any discrepancies. So again, I'm going to let you work on this on your own because I want to make sure you can both follow me and build your own. Okay. Now, having shown you the JK flip-flop, I will note if you had jumped to the D flip-flop, it might have been an easier next build, but maybe not. The reason we do JK first is JK is really the fixed or updated SR flip-flop. So it's natural to go there because really all it uses is one more feedback resistor. So I'm going to go back and point. I guess I didn't point it out. So I'll point it out. All right, we have our internal feedback for our little SR flip-flop, and we take an external. So we actually have 2 connections off the output. So one's going to go off to LED, one's going to go back to this K flip-flop, and one's going to go back to this internal SR. This is basically my S naught R naught flip-flop inside there. So my JK is just an updated version. By doing this universal feedback, we now have the ability to not have an invalid state. We get that toggle state instead. The D flip-flop really just uses it's going to use our 7400 NAND chip again. I have an input, a single input, and the clock goes to both these NAND gates, and the output of this one goes to this input, as well as here's my basic SR flip-flop again. So I can just use my single 7400 chip, and I can go through and label it. And I can go through and power's 14 and ground is 7. So I might just say that's 13. That's 12. That's 11. The other one, I might share this as, let's see, that's 11. So 12. Oops, I'm going the wrong way. 10, 9, and 8. Hop them to the other side where this was probably like 1, 2, 3, 4, 5, and 6 or something like that. And write them down and just build it on that single NAND chip. So what should this do? Well, if my clock is 1, or I can show it as up, this is 0, 1, 1, 0. All right. So this is Q equal to 0, Q equal to 1. You can call them set and reset, or you can call them just 0 and 1. Over here, if the clock is something else, what happens? Well, it stays the same. Actually, no, sorry. Doesn't show that. Made a mistake. It should be the previous value. So you can call it stasis, you can call it previous, you can call it latch, you can call it hold. My concern here is most of you understand it doesn't change. The clock's not going. So you should build this. This is not real exciting because you set D It'll be exciting it's working, but if D is 1, that's 1. If it's 0, it's 0. Run this at 1 hertz and you should be able to see a little delay when it changes waiting for the clock. Fill this out. Should work according to theory. Speculate on the primary uses of the D flip-flop. Feel free to look that up. I mean, they're very practical and very useful, and we will see those in incoming labs. Okay. So now that we've built those out of NAND gates, we're going to take an entire flip-flop inside it, already pre-built in the chip. I'm going to do that in a different video, though. I think we hit 20 minutes, which is about where we want one of these videos to be.